I appreciate you playing along here. Again, we will not cover part 4 in the face-to-face setting, but we'll pick up with part 5 on when we meet again on Wednesday. So we've been talking about equilibrium constant expressions, and there are some other tricks or some other sort of problems you need to know. One of them is what we say solving the equilibrium constant expression. And the way this works is you need to know the initial concentrations of all the species involved, the reactants and the products, and then you need one other piece of information, and that kind of breaks out into two different problems. So you can either know after the equilibrium concentrations, you can either, after the initial concentrations of everything, you can either know the equilibrium concentration of one species, and then we're going to work that problem here in part 4. The other sort of problem involved in solving equilibrium constant expressions is where you know the initial concentrations of everything and you know the value of Kc, or the equilibrium constant. So let's work that first problem here. So again, we're going to be given the initial concentrations of everything, and we're going to be given the equilibrium concentration of one species. This is going to involve kind of backtracking, and in Gen Chem 1 we talked a lot about stoichiometry, so that's going to enter into play here, just kind of some simple stoichiometric calculations. So for example, we could have this chemical equilibria that we've been looking at a lot recently, where we have everything's in gases, they're gaseous phase. We have 1 mole of N2 reacting with 3 moles of H2 to form 2 moles of NH3, and they're in chemical equilibrium, so they're going from left to right and from right back to left again. We could write the equilibrium constant expression. We know we've done that several times, and we'll actually have to do that here in a minute coming up. But what I want to focus on is, we said in this case we were given the initial concentration of everything. Everything is 1.00 moles per liter. Makes it simple, doesn't it? And then, oh darn it, no it's not. Help keep me 100% here. So actually the things that are 1 molar are just the reactants. Notice that the product we don't have any of. So this is nothing and nothing gone, and this is 1.00 molar, sorry about that, and this is 1.00 molar. That's what we call, I'm going to put an I here, that's what we call their initial molar concentrations. At equilibrium now, we have that the N2 has decreased from 1.0 moles per liter to 0.921 moles per liter. Okay, that's at equilibrium. Here we're going to actually, in my ice table here in a minute, that's going to be our equilibrium concentration, of N2. And at hand, we're supposed to do two things. We're supposed to come up with the equilibrium concentration then of the, let's see, that's N2, the equilibrium concentration of H2 and NH3. And then we're also supposed to then, after we know the equilibrium concentrations of everything, go ahead and knock out the equilibrium constant Kc from the equilibrium constant expression. Okay, so this is a solving an equilibrium constant expression. So, oops. Yeah, all right. I think my bills. I inserted a table here in a minute, so it's kind of throwing me off. So we know that if this is an equilibrium, okay, then the equilibrium concentrations, put a little subscript E here, okay, you know, of the product, the NH3, and the reactants, N2 and H2, raised to stoichiometric coefficients, that is equal to your equilibrium constant Kc at a specific temperature. And we're going to hold the temperature constant here. So here we go. This is the table I inserted, and we'll be working more with ice tables, ICE. It has nothing to do with frozen substances, excuse me. It has nothing to do with ice as in ice water or anything like that. I stands for initial, C stands for change, and E stands for at equilibrium. So here's the way the ice table works. And what I do is I go ahead and make these columns for each of the species. So I have a column for the molar concentration of N2, a column for the molar concentration of H2, a column for the molar concentration of NH3. And then I'll write I for initial, so these will be my rows, C for change, and then I'll write E for at equilibrium. Okay, so here's the deal. You're going to start out with something, If you apply the change, you're going to get the equilibrium concentration. So let me kind of show you what this looks like then. We said that the initial concentration of N2 was 1.000, I believe, molar. Okay, the initial concentration of H2 was also 1.00 molar. The initial concentration of NH3, there was none. We said that at equilibrium, well, before I go on, let me kind of show you how this works. The change then would come from stoichiometry, the relative change. So, for instance, if we make the relative change of N2. Now, here's the deal. We talked about this before. The fact that you don't have any NH3 to start out with, you know that this chemical equilibrium is going to have to go from what we say left to right. These things are going to decrease in concentration, and this is going to increase in concentration to start out. Well, it just will to reach equilibrium. So that's why I'm going to actually put a negative x here. Does that make sense? Because it's going to decrease. And I'm putting just a negative 1x because the coefficient is 1. I would put what? A negative 3x here. And I'm going to put a plus 2x here. Those are relative changes. Does that make sense regarding their stoichiometry? Now I'm going to go ahead and write down the equilibrium concentration, which was at 0.91. Oh man, I hate it when let's see. Here it is, 0.921. Remember that number. Okay. So here we go. We had 0.921 moles per liter was our equilibrium concentration of N2. Okay, so can you see what X is then? Based upon that, X has got to be equal to 1.000 minus 0.921. Does that make sense? Well, I got my calculator here. 1 minus 0.921, 0.079. Oops. Does that make sense? That was our change. So I'm going to go ahead and insert that here. 0.079. Now, based upon that change, can you see what this change would be? Well, this change would be 3 times 0.079. And I get, this is going to be a, oh, I should put negative there. This is going to be a negative 0.237 moles per liter. All right, so I can actually go ahead and take the initial 1.00, apply the change, negative 0.237, and I get, that's not what I get. I get an equilibrium concentration of 0.763. All right, cool. So what about this over here? This would be 2 times 0.079. So this is going to be a plus 0.158. So we take the initial, which was 0. It didn't have any to start out with. The change, which is plus 0.158. So we end up with a 0.158 moles per liter. Okay, those then would be the equilibrium concentrations. These actual numbers right here are 2 of the things we were trying to get to, the equilibrium concentrations of the other things. We were given this. Okay, and I know my ice table looks a little scrambled here. It looks a little messy, but it's the right idea. You wouldn't have to use an ice table for this one. We are going to have to use ice tables, I believe, later. So here I do the same thing, kind of longhand. I say that this was your equilibrium concentration of your N2, so your change must have been 0.079. We can use stoichiometry then to calculate the changes in the H2. Okay, the stoichiometric coefficient in front of the H2 is 3, so here's a stoichiometric ratio. The change, as we said before, would be 0.237, excuse me, and that's going to be a negative change because our equilibrium has to go from left to right. Okay, so the amount of NH3 formed, stoichiometric coefficient is 2. Okay, so the ratio is 2 to 1. So we get 0.158 moles per liter formed. Okay. So here's where I finish up the deal. Again, I just think an ICE table is a better way to organize this information. At equilibrium then, our initial concentration of our H2 was 1.000 moles per liter. It decreased by 0.237 moles per liter. That left us at equilibrium with 0.763 moles per liter, which is what we said. The initial concentration of NH3 was 0. It increased by 0.58 moles per liter, so 0.58 moles per liter was its equilibrium concentration. And we're almost done. The last thing that was asked of us was to go ahead now and take these equilibrium concentrations and plug them back into the Kc, or the equilibrium constant expression, and knock out the value for Kc, and it looks like this. Remember, we're going to raise the molar concentrations up to their stoichiometric coefficients. Looks like this. Tap that into your calculator, give it 3 sig figs, and you're looking at a Kc of 0.0610. Okay, so let me know if you have any questions about that. It's kind of a, well, it's a good standard sort of problem, one that would be good for your test.